this program, you can see the program that I written, I choose some of code so that I can only run in Linux. Okay, so this is the Dining Philosopher program. So you will find some similar, something that you already heard about, the down call, the up call. Okay, so I implemented myself. So later on when we talk about the threading program, multi-threading program, I will also release this code. I implemented using multi-threading. Okay, so you will find some of the thing left, right also happen in our solutions. Okay, so today we will talk about this. So last time I talked about the preview of this program or this classic IPC problem. How classic it is? So it is going to talk about a very not fairy, but a daily life program. So the daily life program is that we have not just a square, maybe this is a circle. I drew a circle badly, right? You have several rows coming in, okay? And just like that, you are going cycling, choose the exit to go out. If you're going to design a traffic control pattern over this, okay, you will need the Dining Philosopher solution, okay? So I keep this drawing here first, so that later I can talk about this using this drawing. So it's always talking about something here. So this is my drawing, You know how bad I am, So I can later on I scan my secondary school academic report. You will know that my art subjects fails for several years. Okay. So this is a car, okay? Yeah, this is a car, so that you see the direction, okay? So we have 4 rows, all rows single direction. So this and this and this and this. So we will have a big problem if we have a long big trunk, which is wider than this length for n coming in. Okay? So when we observe this problem, basically it's very similar to the Dining Philosopher. So when you look at this problem, can you at least find some of the area that require mutual exclusive access? Mutual exclusion. Where is it? Can you find some mutual exclusive access? And how many? If I talk about this problem. You think no? At least there are some crossroads here, right? Why we need mutual exclusive access? Yeah, very simple. Are you allowed two cars to touch together? No. Right? Let's say there's a car coming in, there is also let's say this area, another car coming in. Okay, so this car goes in this direction, and this car goes in this direction. You will have trouble if we allow them sharing this area, sharing this area. So a traffic light or air control is to guarantee mutual exclusive access for each pieces of this block. Okay? And later on we will go into the detail in looking at, hey, for a car to let's say they don't turn, they just want to go straight. Okay? How many items you will need? Yeah, by looking at this, you will immediately find that, okay, for this car called A, okay, you will need a mutual exclusive access if it's long enough of area, alpha, and beta. Right? Mutual exclusive access at the same time if it is long enough. Let's say there's a shortcut, for a shortcut you need a mutual exclusive access for alpha first, and then you can release alpha and take beta. And I need a traffic light control to allow me, but I cannot assume the length of the truck. Okay? So when the truck is long, then alpha and beta access, we have to take it together. Okay? We have to take it together. And the Dining Philosopher problem is exactly the same like this. Okay? Last time we talked about a brief introduction to this problem. This problem is actually we have this table. Okay, this table has 5 spaghetti. Okay, so we assume infinite supply of spaghetti, and each guy who wants to eat the spaghetti, they need 2 forks. Okay, need 2 forks. Similar to the crossroad puzzle, right? Crossroad, not crossword puzzle. The philosopher plus the wrong couple need two mutually exclusive sets of the area, just like you need a mutually exclusive sets to these two forms, right? You won't share the form, right? Let's say, I take one spaghetti, okay, I share the form with you, and then you take another one, okay? No, okay? We won't allow the sharing, okay? Each form is a mutually exclusive set, okay? And that's why we say that the form are actually shared object. Okay, each professors or philosopher, whatever you want to say, they are processes. They want to take the mutually exclusive ownership to this form temporarily, so that they can eat for some time and then release them. Okay, and when you release them, then another process or another philosopher can take the form. Okay, so I give you some illustration. So let me number the form. Okay, so for the sake of an easier illustration, process 0 up to process 4. So we have 5 processes, and we also have 5 forks. Okay, so I name them 0 to 4. So for the sake of an easier talk, okay, generically, we will say that philosopher I will need the fork I as well as I plus 1 present A. Okay, so this guy needs 0 fork as well as plus 1. And this guy, number 2, needs 2 and 3, so it is its number plus 1. And how about the number 4? Its number plus 1 present A. A is 5. Okay, we have 5 forks, so present A, so that 4 plus 1 is 5, 5% 5 is 0. So this is a modular arithmetic only. Okay, so get this idea. So we assign each fork, okay, so they cannot say that, oh, fork 0, okay, is owned by philosopher 0 now, and philosopher 4 cannot take this fork. So how about we can seize fork number 3? No. Okay, we assign this ownership schemes to each process. So you will expect the following. You will expect the alternate philosopher usually will eat in parallel, right? Because this guy owns the 2 forks here, and alternate philosopher won't share the fork with you. Okay? Now this is adjacent, so they will share the fork with you. The alternate one will never share a fork with you, so we usually observe alternate philosopher share go parallel with you. And in this setting, because we only have 5 forks, and in parallel, if we allow 2 philosophers to go together, it will seize 4 out of 5. So the remaining one cannot allow any philosopher to go to eat spaghetti. So we will only have 2 guys running parallel most. Okay? And this setting can change. This setting can change. Let's say we can go up to a 6 philosopher with 6 forks. Then you will have 3 philosophers going parallel. 7 philosopher with 7 forks, still 3 philosopher going parallel, and you can do the counting. Okay? And this solution just focuses on 4, but later I show the code. It is scalable from 3 all the way up to infinite. Okay? So now you understand the scenario for the allowable case. For the forbidden case is this guy. The forbidden case is the adjacent guy want to start eating together. Okay? So they will take his number, let's say this guy take number 3, this guy will take number 4, but so happen that this number 4 is required by the 2 adjacent guys. So these 2 guys cannot go in parallel. Okay? And our solution is not to resolve this conflict. Okay? Yeah, they will fight and punch each other. No. Okay? We want to avoid this. Okay? We want to avoid saying that, hey, let's say philosopher 3 already took 2 forks. Maybe philosopher number 4, please wait for a moment, but don't punch this guy in the face and take his fork. Okay? So we want to avoid conflict. As in the cost reversal, we want to avoid car crash. Okay? So here is the scenario for the forbidden case. And now let me show you a very naive approach, and you tell me why this doesn't work. The naive approach is we just want to guarantee mutual exclusion. Okay? And yeah, let's say no one can steal the fork. Okay? And our proposal is when you're hungry, you try to check if anyone using the fork you need. Very simple, right? I want to check, where the forks are available. Then I will eat or not, I will wait. But how to implement it? Simple. I set up some function call. Okay, the function call you can treat it as down call or up call. Okay, so this takes some time to understand. So I create 5 semaphore because I say that I want to guarantee the mutual exclusion. So for mutual exclusion, if you still remember the producer-consumer model, we will treat every fork as a binary semaphore. So that if you own that fork, I will decrement the binary semaphore from 1 to 0 so that another guy can take it. Okay? So this quick question should be the initialization value is what? It's binary semaphore. And then what is going on here is I will take 2 consecutive down call on over different fork. Okay? So I'm a philosopher I, okay? So I will take the fork number I, as well as I will take fork number I plus 1 modulo n. Right? Then after I finish eating, I will put down the fork. Okay? The fork that I put down is also the 2 numbers that I pick in. So why is put fork? Put fork. Okay, that's very wrong, right? Okay? So this just translates into the down and up call. Okay? Can you tell me an execution sequence that you get trouble? This is a problematic code. Okay? And should not be allowed to be executed. Can you give me an execution order that we got trouble? Yeah, talk with your neighbor. I give you 1 minute. Problematic. Yeah, it's very intuitive, right? Just like a normal human. You can also think of it in a normal human. Okay, you find 55 people here, see the circle, put down some pen to animate it. Yeah, you can also play the game with 3 people. 3 people also work. Okay, 3 people, 3 pop. Okay. Don't do it 2 people. 2 people only share 1 pop. No meaning. Okay. Execute the sequence. Then you get a problem. You get in a trouble. Anyone here? Any idea? You have got any idea? No. Okay. You have any idea? No. Okay. How are you? You have any idea?
If everyone take 1 vote.
Everyone take 1 vote.
Then they will stop waiting.
They will stop there waiting for someone to release it. Yeah, that's correct. Very good. Thank you. Okay, so can you hear this idea? The idea is very simple. You can animate it with your friends. Okay, everyone put a pen on the table. You imagine that you're in a circle, just like we have 6 guys. Very good. Okay, you 6 guys put down a pen. Okay, and you cannot pick this box. So sorry. Okay, and everybody take your pen up. Okay, you pick it up. Then can you still find another pen to pick up? No, you run out of all the pens or all the fork, okay? You just pick up your own number, and execution sequence is very simple. Just like this, okay? You allow the code to run up to line 4, finishing line 4, then you execute and take your fork, your number, okay? And how about the adjacent one will always be taken by another guy. And by the design of the binary semaphore, the semaphore value goes to 0. Okay? You want to take the fork, and the fork is so happen get the semaphore value 0, you will go to sleep. Then every process will go to sleep. It doesn't work. That's the word. Okay? Any other ideas? Any ideas to resolve this problem? Okay? You think of it in real life. Okay? You just so happen you get 5 people for 5 chopsticks. Okay? And if we get rid of the problem that is not hygiene enough to share, okay? You think of a way, okay? 5 people, 5 chopsticks. If I allow this to happen, it will very boring, right? To pick it up, okay? No one can hit it, okay? If so happens this is something that you can use 1 chopstick to eat, then that's okay. But no, you need 2, right? Then what should you do next? You cannot go on. And how about let's imagine a case that, okay, I find that this is the case. Then I put down. Okay? And wait for a while. Okay? Or you communicate with your partner saying that, hey, why don't you put it down? Okay? Then your partner will say the same thing. Hey, why don't you put it down? Okay? Yeah. I mean, let's imagine that every people will be polite enough, okay, and invent another protocol. The protocol that I want to invent is, I don't show you the code because I already showed you some of the HTML sequence here. Okay, the illustration here is the idea of putting down. Let's imagine that I want to pick up 1 fork, okay, and then I find some problem. The problem is actually I cannot go on. Okay, so how can I know that I cannot go on? Let's take a look at the code. I will check if the next fork, the line 4 here, is used or not. If it is being used, okay, I will call up in order to animate the action of putting down. Okay? Putting down. So I pick up the fork, I find that the next fork is using, put it down. And sleep for 1 second. Okay? And after 1 second, what should you do? You will, because of this example, so we will go here, look back, and check whether I can take up my fork again. Okay? So this is a very funny scenario. Okay? So we will have a chance. I don't say that the chance is high, but the chance is like this. Okay? This is the fork. Okay? Originally put down, I pick it up. I cannot go on. Put down, pick up, put down, pick up, put down. Yeah, just like stupid guy, okay? Yeah, just like doing that. Yeah. Is it possible? Yes. Yes. Okay? Because you're deterministically sleeping for 1 second. Okay? Everybody sleep for 1 second. Yeah, pick up. So there are some solutions, some lousy solutions to say that, okay, we don't sleep for 1 second, random number of seconds. Good. Okay? But you didn't eliminate the chance. That you will go on with this. Okay? Put down, okay, put down, okay, take it out, okay? Yeah, just wasting energy. You are hungry, still wasting energy. Okay? Yeah. Don't do it, okay? And this is the solutions that if we still think of this fork is a sample, okay? So I will give you a solution that will turn the game around, turn it upside down, okay? We don't think of the solution as so physical, okay? I don't imagine that each fork is a sample. We go back again to take a look at the solution required. So go back, and come on. Okay, so the solution requirement is actually not about a fork. Okay, we can eliminate them. Okay, and imagine again, how should I formulate the solution? And actually, this is about 5 guys working together, but never allow adjacent guy to work together too. That's all. Right? It's not about fork. It can remove it. Okay, the fork is just there to fly your mind. Actually, you can think of it this way. The other guys that can eat never an Asian guy. Okay? Now, this is the insight. And with this insight, how can you invent a solution? It may become totally upside down. There is no fork again. I just check what is the checking. whether the adjacent guy is eating. If it's eating, I should not eat. If I can guarantee that both my left and right are not eating anymore, I can go eat. Now, does it make sense? This guy, before he can eat, it will check. 0 and 2, are you eating? No, then I stop eating. Then maybe philosopher 2 go into the game and check whether philosopher 1 and 3 are eating. Oh, you two so happen are both eating, so I should not eat. Until when? Until these two guys are not eating at the same time. Then I can stop. Okay, so this is the insights. Okay, and by this insight, we can invent a solution which is widely implemented. Okay, so this is my insight. I already talked about it. This solution. So what is this solution? I will break it down piece by piece. Don't worry. Okay, and you'll find the exact codes that I've written in my Linux. So you can find the put fork. I just changed the name. One down, one up. Okay, so go back here. The put fork, one down, one up. So I can map it and implement it deterministically and without any random. So let's take a look at piece by piece. Don't worry. Every year people get a sense that I think that I understand when I final examination they do that. I understand. Okay. So let's go. Here the first part, shared object. Okay. So shared object is actually remembering different things now because we don't need the fork anymore. Okay. So I will implement a global array, a shareable array, to implement what is your status, right? I want you to remember, hey, whether you are eating, or you are sleeping, or you are in somewhere inside the section entry, or somewhere inside section exit. Okay, so I want you to remember where you are. So we implement a state array, which is shared, and which is just a normal variable. Now with this guy, then we actually need some protection. The protection is the mutat. Okay, we always say the mutat is actually a protection or mutual exclusion, and it is binary semaphore. So I will try to set up one semaphore only to protect the entire array. Okay, so this array is being protected. Now, how about this? Later on, I will tell you what they are. Okay, they are very interesting guys. Okay, and I leave this question here blank. Okay, while I'm talking about the things, you tell me what should be the initialization value of this array of semaphore. They are not binary semaphore, they mean something else. Okay? So this is will be free state eating. So you are in the eating progress. So you are in the fourth line, fourth eat. Okay? You may have a status called thinking. So the thinking will be of this status. And there is a special status called hungry. So where can you find hungry? It's actually within the section entry. When you get into the section entry, I need to know that you are in there. Okay? So I set up a special status here called hungry, and every philosopher get an ID called ID. So where can you find ID? It's here. The philosopher ID. So you can imagine that I can range from 0 to 4. Okay? Then this is the protection on line 2 over the entire code. And the entire code, why is needed protection? Take a look. I assess the state. So I need the protection starting from line 2 to line 5. Okay, from line 2 to line 5 to protect the whole range of code because I assess in share variable now. Now, this share variable only updates in line 3 as the same time we have a helper function. I usually call it helper function, but in most textbooks it's called test. Okay, well, usually called test doesn't mean anything. Okay, but in this solution, the test itself is very important. How important it is? Let's take a look. It will change something and also read something. Okay, it will read its own status. It will also read the status of its left guy and right guy. So what is the left and the right? It's actually two macro. to macro to, you put an I there, okay, I will calculate the number of your left and the number of your right. Okay, so on the right is easier, +1. On the left is minus, used to be -1, but we have a problem that after -1 you will 0 -1 get into trouble, become a blank number. So I add n there in order to rectify that. Okay. So here is the macro I put out there so that for each I will calculate your left position and the right position. And this statement together makes sense. If I'm hungry, as well as my left is not eating, so maybe my left is start executing a hungry statement. Okay, this can be later on you tell me when it's possible. Okay, maybe it is already start changing to hungry or I don't know. But as long as this guy is not eating and other guy on the right is not eating, I declare myself eating. I declare myself eating. But declare myself eating doesn't make any sense, right? We need one more control. The control is, I don't know why, I do an up semaphore here. I do an up semaphore here. I don't know for whatever reason. And these two come in a pair. Okay? So keep an eye over this two call. We will have a chance that this if return true, then you can do the up of this semaphore and then pass through this down. Or we fail this call. What is the circumstances that I fail this call? Let's say my left and the right so happen that they are both eating. Okay? Then I will fail this check. If we fail this check, what is the meaning? The meaning is I cannot get the access token or access card. This is actually the access card to enter into the table to get eating. I missed that access card. I didn't get the access. So when somebody check my identity, oh, are you being authorized to get in? So sorry, I don't have the card. You go to sleep. If you get past this test, I will give you the access card. Call it up, I give you the access card, so that you can later on use that access card to go into the group and start eating. Yeah? So tell me, what should be the S initialization method? If you understand what I said, I give you 3 choices. 0, 1, 2. Don't ask me, hey, is there any minus 1? No. Yeah, no negative number. Yeah, do I say it again? It's actually as an access card mechanism. Okay? If you don't patch the if case, then I give you the access card. You can use the access card to start eating. Maybe you cannot grant that access card because my neighbor is eating, so I miss the access card and go to the identity checking on section 896, the down call. I fail. Then I will force to be sleeping there until someone gives me the access card. Later on, I will tell you where I will get the access card. So what should be the initialization value? So then there's 0. Okay, 1. Yeah, my example is 1. Anybody choose 1? No. 2? Of course not. You never heard of 2, okay? So either 1 or 0, it should be 0. Okay? It is a reverse use of the binding semaphore. We reverse it. Okay? You start with 0 and hope that people will give you the access. And here is the moment that I get the access, and then I immediately use the access. Okay? So this is the access token mechanism. We did another way to implement it. So I said is turning your concept before upside down. Okay? Before is a visual exclusion. I already set it to 1 so that it's unlocked down. I turn the lockdown. Now here is the reverse. Now where can you get the access card back? Okay, let's say I'm so unlucky that my left and right are already eating. I cannot go on. Then I will be blocked at the slide 6. Who rescue me? Of course your neighbor, right? Your neighbor will rescue you. But how your neighbor will rescue you? This one. This one is very interesting. How interesting it is? Let's take a look at. Of course, we will change some states or observe some of the states. So we will need to protect all the access of the state here. I3, I5 also will use the state variable. So I will set up a mutual exclusion set there. Okay. Then what happened to these two tests? These two tests is interesting. Okay. You actually generate the number. You are the one who want to stop eating, right? You stop eating, you want to put down the fork. So you, on your behalf of your left guy, okay? So I need to draw now. Okay, clean this up. So you are the one here, the two guys are here, okay, 5 guys, so you are the one, okay? You're the one here, you want to put down the fork, so you are pretending to be the one on your left. So this left, this is right. So pretending to be your left and ask, hey, are you hungry? Are you hungry? Hungry, actually, okay? Are you hungry? If you're hungry, good. That means that you want to go in. Okay? And I will, on behalf of you, okay, I change direction, okay? Your eye is here already, okay? So this is an eye, okay? Look at our eye. You know why, okay? So you look at it in this way, and what is your left now is here. What is your right is here. Okay? So you become the one on your left, on behalf of it, check the left and check the right. And the story goes with the code. With the code line 4, you pretend to be the one on your left and ask the left of your left. Are you with me? And who is your left's right? This is you. Okay? So this guy is you. The right of your left is you. Okay? Also for the, okay. I got stuck. Okay? This is the left is the left, the right of the left. Okay? I go crazy. Okay, I use the board. Okay. So, oops. So this is you. Okay. This is your left. This is your right. So the core will check the left's left. Okay. And the core will also check the left's right. So that means one of the guys is guaranteed that it's not eating. This is you. Not eating. And it depends on luck. Okay, I don't know whether this guy is eating or not. Okay, so you will check. If you pass this check, what will happen? If you pass this check, the left and the left right, okay, is allowed you to go ahead. You will up the semaphore of the left guy. So what is the meaning? The meaning is you actually put down a fork and enable this guy to eat. And at the same time, your right, okay, may be also blocked there. So you will ask, hey, Mr. Right guy, your left is eating or not? It so happens to be you. And how about the right's right? Right's right here. Okay, so it's this guy. So if both guys are not eating, then this guy is also saying yes. Okay, good. For we will start eating. So this anyway 1 point is when you put down a fork, you can actually allow your neighbors, both of them, to start eating together. Right? Can you see this? Maybe you are the one who blocked these two guys. Okay, these two guys are not happy. Okay, not eating. So you are the one who blocked these two guys. And when you put down the fork, you execute the two codes in order to allow both of them to be happy again. Okay? Yeah. Good job. So this is the magic of this test call. The test call is actually pretend to be another guy to get the access token, and the access token will eventually allow the other guy to get rid of the block. Now you may have different problems, okay? You formulate a bit in your mind, I give you a break, okay? This is a long path in order to reach this solution, okay? And then after this, I will ask you 1 or 2 questions, okay? It requires you to understand the code, okay? Then we will go on to the next few slides, actually to animate the solution. Then I will show you crossword puzzle, how it's being solved. Okay, so let's have a break. So this is the big solution. Now, I said that I have several questions for you. Maybe I do it one by one, and depends on your feedback. Okay, when I choose to continue to say others. Okay. Now, let me ask you the first questions. Okay. The first question is, by calling the put form, we can rescue our friend, right? Our friend of God. Okay. So I rescue them. In the sense that I call the up call, so that they originally get blocked here, I rescue this. My first question is, tell me, is this possible? It's possible that, I don't know why, my friend should be going to sleep because of going through this test. Okay? So it should go to sleep because it's failed to get this. Okay? Can we have a context switching after the line 4 finishes coding, and then line 5, before line 5 we have context switching, and then I go to a trouble. That, I don't know why, another process start the put form. Then we have some trouble, right? Why is trouble? Because previously he said that, okay, I want to do the up, and then I want to fail to do the up, and cause the whole thing get into trouble. Is it possible? It's possible that, or I should say put it in that way. Can I have 2 processes, one inside take form, doing some change, calling the test, and other one calling put form, doing some change, changing some value for value? If yes, we will have trouble. Why? Because we're animating the things that I put down the form, rescue other people, and other people, please don't touch those form or those status. If you do this, I don't know what will go on. Okay? So my question is it possible that we have 2 processes going in parallel, and so happen that they are changing the state here simultaneously? Will they yes? Will they no? No, then why? Give me the reasons. No, you don't say anything. What is your opinion? I'm happy. Okay. So how are you? You're not saying anything. This cannot, okay. And mutex, or which line? We have many mutex here. Session entry here. Line 4, execute line 4. Yes, okay, so the mutual exclusion setup. Okay, mutual exclusion setup. So remember, there is no case for 2 processes going into the session entry or the session exit, or even some different combinations because of the mutual exclusion setup. And this mutual exclusion setup is not just protecting the state array, it's also protecting the chance that you grant the set token to your friend. Okay? So this is question number 1. Question number 2 requires you, if you have pen and paper, okay, this is bench. Okay, if you do not, okay, use your mind to think about it. This is usually a typical question in the final exam. What if these 2 lines got interchanged? These 2 lines, the take form 5 and 6. They are interchanged. Okay. Will I get into any trouble? Yeah, you don't need to give me an execution sequence. Just give me a sense where you feel, oh, is it problematic or it's not problematic. And feel it about it. I give you 2 minutes in order to feel it. Remember why I asked you the first question. The first question is kind of important. I asked you the first question, and then I asked you this question. Yeah, if you have pen, paper, okay, or you want to borrow this stuff, okay, I can lend you, okay. But I will project your writing. Hey, give me a high level idea. You don't need to really think of, oh, the code is this, get into some trouble. Any volunteer want to say loud about this? By the way, let me do a simple polling. Who think that there is no problem? Only one, no problem. Okay, let you take care of one. Okay. Who think that there is a problem? Okay. More, but okay, Jason, I give you the like. Why there's no problem? You tell me. But what is the meaning of no problem?
That would not be deadlock.
No deadlock.
It may be slower.
It will be slower. So this is your iteration is slower. Okay. So and not only one guy say that no problem. So for have problem with raise of your hand, say have problem. When you raise of your hand, right? Then there's a problem. So what's the problem?
If the test you didn't up the SI, then it will stop in the down SI forever because the mutant is locked and others can't go into the process to free the.
Okay, so you have some prerequisites. The prerequisites being some people already caused it down. Right? It's possible that there are some people before going into the eating stage. Is it okay if let's say the scenario only have one process? Okay, that process go into eating. Okay. So this is the prerequisites. So everyone gets it up. The prerequisites is if I change the order 5 and 6, does that cause any trouble that I only have one process? No. Right? The only process can go down for the checking and get broken, and eventually the download won't stop it. Now this is the prerequisites. Or not? Yes, because we have to kind of inject a process so that the later process get in trouble cannot get broken. Right? Then we'll go to your statement. Your statement is
when others
your neighbor. Let's say your neighbor
is eating, and so I didn't have the SI.
So S means the
later
box down the box in bottom line 4.
Yeah. Yes.
So you cannot go to the line 4 then.
Then I have to down and I have to wait.
I'm down and wait. So you are talking about session entry.
Yes.
The new line 5.
Yes.
The new line 5. So the interchange.
I have to wait so the mutex isn't open.
So the mutex is what is the value when it goes down?
It's still 0.
Still 0. So for other guys, okay.
They count down the mutex.
Okay, but I give you the questions. So the prerequisites is there is already some people eating, right? Then those guys finish eating can come back and do something, right? And execute the section exit. Is it allowed? Those guys finish eating already, And because you're down, right, I come to rescue you. Yeah, this is not an easy problem. No. I come to rescue you, yeah. So any people want to help him? So he's got stuck, okay? He finished half of the story. The prerequisites of the story is somebody get through all the code and go to the eating state of the philosopher. Then the philosopher, let's say this is number 0. Then number 1 comes in. When number 1 comes in, it will go down. Okay, so you got the answer.
Because they can't rescue me, because the mutex is down. Only the mutex is open, they can read the
So
text.
which one you're talking about?
In the section exit.
Exit?
Yes, in the second line of the green box.
Okay.
And when they down mutex, they fail.
Okay, good. Thank you. So you got the correct answer. Okay. So anyone want me to repeat, or you already get lost? Yeah. The problem is the one that cannot get access. Okay, because the adjacent people already eating, so you cannot get access. You will call this downfall. Okay. But before you call it downfall, you go to sleep. You remember to release all the semaphore that you hold. Right? So the original code here is you release the mutex before you go to sleep. But I reverse it. So you will sleep together with the mutex. So you lock something as if you are sleeping in the toilet. Will you do it? I don't think so. It's best time, huh? So you understand what we have. Okay, so then here when you go to the food fall, okay, somebody wake up from finish eating. So want to rescue you in order to help you to give you the token. That guy cannot proceed either because of this down mutex. This down mutex, the mutex already, you take the mutex together with you. You are the only one that is able to call the up mutex when you are going to sleep. So when these two lines got interchanged, you will have a deadlock. And a deadlock is not so simple. You need some prerequisites happen, and you are the one that get jammed. And when you get jammed, other people cannot get in as well because you get the mutex. Okay? So these are the two answers, two questions that I want to ask you. Okay? So the remaining animation is just to animate the case that what happened if I have a thinking hungry. Okay? So I hope that you can read it by yourself. This is just a simple animation, animating over the code. Now I want you to understand another problem now. Okay, it is one of my midterm examination. I set it up at 200, and that year we still have midterm. Okay, the midterm is actually killing people. I want to set up a very difficult question paper. Okay, to say that they say that I'm too weak. Okay, I need to improve. Okay, then I adjust the final exam paper so that it's easier than the midterm. And everybody feels very good. Like, I have improvement. It's actually under my control. Okay, so you feel that you're good because I control that. Okay, so the traffic jam problem. Yeah, again, okay, this is the bad thing about this board. It cannot save my previous story and reload it. I can save it, cannot reload it. Okay, so it's actually the same for the puzzle here. It's actually a linear philosopher problem. So what is linear philosopher problem in this setting? Yeah, so let me draw the arrow first. This, and then this, and then this. Okay? So if we don't control the traffic, we'll have this deadlock scenario eventually. Okay? So this is deadlock. Now, if we want to control the traffic, at the same time we want to improve the concurrency. So what is the improved concurrency? Basically, we can do a very simple test. Okay, every city. Okay, I see many cities. I see a whole Hong Kong traffic control. It's actually doing a one model, right? It allows this to execute first. You mean that like the car to go straight, and then let this to go straight, let this to go straight, and taking round robin turns. This is not having the highest concurrency. What is the highest concurrency? In this setting, is to allow two parallel rows to go together, right? What does it mean? You let this and let this go together. Do you cause any trouble?
But in real case, people cause trouble.
Yeah, what?
It can turn.
Oh, no, we reject the turn case. Don't turn. Yeah, don't turn. If we have turned, we have a very out. You ask a very good question. That midterm exam paper, the next question is, what if we have turned? What if we have turned? Can you change the solution? Yeah, let's put the turn aside, okay? Let's imagine there's no turn. Then we allow the highest concurrency is allow these two rows to execute together, then stop for a while, another pair to go together. Okay? So what is the meaning of having together? Let's imagine that this guy is called philosopher A, this guy called philosopher B, philosopher C, and philosopher D. Can they eat together? Actually, the control is alternate rows execute together. Okay. Adjacent rows execute together. No. Is it the same as studying philosopher? Exactly the same. Okay? The exactly same scenario for studying philosopher. That's why if every C implement this, okay, we will have a high throughput. Let's say that this scenario will be allow A and C to execute together. Then you will have B and D execute together without any problem. Okay? Now, what if you have turned? If you have turned, we will have big trouble. Okay? If you have turned, let's say that A will turn in this way. Actually, I remember I can change the color. Change the color, stroke color to, yeah, this. Let's say I allow you to do this turn. Okay, allow you this turn. Then the problem is more terrific. The terrific thing is not just the one adjacent to you have to block him out. But the one, let's say you allow the turn for once. Okay, turn for once. Turn left. Okay? Then C execute will block B as well as blocking A. Okay? So if you allow the turn is twice, then you seize the entire city. Okay? This is your playground. You go ahead. Yeah, because you're blocking other ways together. So this actually can scale up. Scale up to what? In the exam paper that I set up is actually the pentagon. I set up a pentagon row. I forgot how to draw it. Okay, I drew it for 1 hour in order to draw a pentagon to let the people know that 5 Tiny philosopher. Okay, yeah, I should draw a square so that I can spell out the people. Okay. Yeah, when 5 every people know that it's tiny philosopher. Okay. So this is the pentagon. I forgot how to draw it. Okay, very hard to draw. Okay. Later on, maybe I share the 2009 midterm paper. Then you will see that, actually it's the pentagon. Okay. So this is the tiny philosopher real application. Okay. And actually, we can write a program to animate it. Okay. I just write a program. You can see I also code the same thing. Let me go to TikTok. The TikTok first down the mutat. Okay, to protect the shared objects, the state. I don't call it test, I call it helper, the helper function. And after I have it, I draw something, so I put a drawing statement here. I want to draw something. Okay, and the down, the up protect all things inside. And after I finish the changing, I will take the access token. And where you will get access token depends on the helper call. So I also implement the helper call in here. So if you're hungry with your left is not eating or right is not eating, you go to eating and call it up. Okay? So I just implement everything that include in a PowerPoint, and the results is something like this.
Oops. Come on. Okay, philosopher. Well, what else? What else? It's interesting, right? So you can see the execution is like this. Is it running out of battery? I think so. Yeah, just like normal people, is get hungry, it will make sound. Yeah, I need to change the battery. All right. Hello. Ah, yes. And you know, CHK stuff sucks, huh? All right. Yeah, you know it is recording. I also see no problem. Okay. So you will see that this is my program running. You may not understand that what is going on here. It's actually the T means thinking, the E means eating, the H means hungry. So I just animating. You can observe that. Hey, do I find three eating together? You will never find it. Okay. You will always find a non-adjacent philosopher go to the eating state. Okay, there's no other cases that is allowed. So this is how I implement it. Okay, and actually I make it very hard to join. You know, join just like the circle. Okay. All right. So this is the dining philosopher. So do you have any question in your mind about dining philosopher? Yeah, I think it's quite clear, right? I should not say this, but I think that the way that I teach is giving you real example, right? So with a purpose, then you know what is going on, okay? So you won't find this application in any textbook, okay? I don't know why. Suddenly I always inside the toilet I think of something interesting, okay? While I'm taking shower, I think, oh, actually this is the same, okay? As a crossbow. Now, we go to the last problem. Okay, so what is the last problem? The last problem is, do you hear me? Sucks. Again? Hello? Hey. Okay, I have to stand here. I feel it's just like jail here. Alright, so what is that? Read-write problem. So read-write problem is very, very close to what you see in Fluent 7.0, the database course. So the database course is have a select statement, has a update statement, insert statement, so and so forth. Okay, you never heard of. There is a problem because you are the only user. Okay, so you are the only user. You are typing the SQL statement, but in the real stuff, you will have a reader, which are let's say the web program that receive data query and other web program doing the data updates. They may come together. Okay, so the database has a control. They classify your statement, whether a statement considered as a reader or a writer. So usually we will allow reader to go in parallel. Yes? Do you have any problem over this? If I allow reader to go parallel? Should be okay, right? Because you just do read-only text. I allow 10 people to read the same table, no problem, okay? But do you allow writer to go in parallel? Usually not, right? I don't know whether your write will have another write to go in parallel and give me race condition, right? This is about the race condition problem. So the writer actually should have mutual exclusive access to the database. Okay, and this is the animations that I show here. You own the database. Okay, actually you own the database during the time that you update the database. After update the database, other reader can get the up-to-date data. Okay, and how about a set of reader reading the database? You will do the other things, but some things goes different now. Every reader is not doing a mutual exclusive access. It is a group of readers doing the mutual exclusive access. It's a group. Okay, you know, I don't know why. Okay, some people love to ask people, hey, let's go to dinner, but without other people go, they don't go. Okay, yeah, here is the same case. Let's go together. Okay, so these guys go together as a pack, and not anyone owning the database, but they form a group here. So this is what we need to uphold. It's not a simple mutual exclusion problem. Okay? So we can generalize it with 3 rules. The number 1 rule is while reader is reading, other readers can go together. So this is definitely not mutual exclusion. It is a concurrency control. If we have reader is reading, then we should block the writer. It's because of the mutual exclusive access. The last is also mutual exclusive access. Now, if we want to implement such thing, it's very easy, right? If we only allow 1 reader and 1 writer, just set up a semaphore called database. Yeah, you get a semaphore, you go in, do whatever things you want to do, and leave the database up the semaphore from 0 to 1 again. Okay, so this is the very simple control. Now, what happens if I allow a pack of readers to come in? That is a problem. And usually, okay, we want to keep track of how many readers we have. And then that's why we set up a shared object. Okay, the object is actually an integer to keep track how many readers are there. Now, let's take a look at the code. Okay, seems to be different colors. Don't look at the reader yet, look at the writer first. The writer is very easy. Just a simple mutual exclusion demonstration. You write the database before you write it, okay, just do something else, okay, and then you do the down call so that you can get the mutual exclusive access, finish all the things inside the critical section, leave it with the up. Simple, okay? So can you find the trace in a reader? We can find it, okay? You can find the down database, down DB, the up database here, down at the up DB, but when you do this, you need to do something else together. What is the meaning of saying something else together? You have to check how many processes go together with you. Okay? So the control is very easy. If you have a down mutex here, then immediately you can think of, oh, this is for mutual exclusion. Now this time it's not the mutual exclusion on the database, but the mutual exclusion of a new integer. So the integer here is called recount to count the number of reader. Okay, we'll start with the initialization value 0. So that means that in the beginning we don't have any reader. Okay, and here the mutual exclusion for the database. So we have db equal to 1. Mutual exclusion for this variable. So also set it up to be 1. So they both are binary semaphore. Now how about the reader implementation? The reader implementation is easy. You want to increment the reader count before it, protect it using mutex. Okay? And if after the change it is 1, that means that you are the first guy. You are the first guy. You are the first guy to enter this cache room. Please open the lights. Yeah, please open the light, but here is not open the light. It is down the database. Shut it down to block all writer to go in. This is our room now. We are readers, okay? And finish the change. Then you should release the mutex. What's next? Next is mutual critical section code. After critical section code, change the reader count again. Now, if you are the last one to leave the room, shut down the lights. If you are the last guy who leave the room, you should declare that you want to release the database access to your writers, So you will up the DB to state that no more reader in. Okay? So this is the algorithm. Any questions? Or you find something wrong, something not comfortable with? Let me ask you, what if we have a stream of reader coming in, and the stream is, let's say, 1 million reader, 1 million requests, all read. How about the writes? The write is very painful, extremely painful. You have to wait. Oh, is there still reader? Okay. Actually they don't know. Okay, because they are sleeping. No, they are sleeping here. The code. They are actually sleeping. Okay, the writer is sleeping, and no one wake him up until 1 million reader finish reading. Then you can write. Okay. So this is the very simple implementation. There are implementation doing this. Doing this is, I want writer to get not a higher priority, I should say, is when I enter the system saying that I start executing my code. I want someone respect me. Hey, I come here first. Okay, you guys, you are the later coming reader. Wait for me. Okay, don't stand in front of me. How can we do it? Do you understand what I mean? We want reader, okay, to come in, no problem. But we have 1 million, and let's say after finish executing 10 reader, a writer comes in. So the 11 and 12 and 13 reader, you should not execute before the writer. How do you implement it? How can you implement it? Okay? So I don't give you the code. This actually was okay, some years ago, one of the midterm questions. Only 2 people get it correct. Only 2. Okay. The first guy is already a Google engineer. He has a first mark, so he solved it during the time in the examination. The second guy, so happened that he guessed I will make these questions. Okay, and before the midterm exam, he asked me, hey, did my questions, did my answer correct? I'm forced to say yes. Okay, then yes. Then he, oh yeah, very good. Then only there's 2 guys get it correct. Yeah, you know, Chinese people love to do it, right? I guess what should be the question? I guess it's correct. Yeah, okay. Only 2 people get it correct. Okay. Then every year, since that year, people come in and always say, hey, what is the solution of this? What is the solution of this? Okay. So let you guess. Okay, whether this year we'll have this question again. Okay. So the IPC problem is kind of horrible, right? To you, it's actually a new type of thinking. The new way to think of an algorithm, executing together with different people playing in the game field. Okay? How can you stop people using semaphore? Now, you may have some puzzle how to implement it, right? You can see my code already. Okay, you can see my code already executing very nicely. Actually, what I'm doing is actually using a library called POSIX Threads, which is available in C and C++. Okay, in Java we will use another thing. Okay, for others it depends. Okay, Python no, or Ruby no. Okay, but JavaScript sucks. Okay, I mean JavaScript don't even have thread concept. Okay, they need another thing called worker to do it. Okay. So this threading is actually very important, because when you're going to write Java program later on in Fluent 0, you will face it. Okay, I definitely guarantee that you will need some kind of control. Okay, so in the coming class, that means next week, we will talk about threading. Okay, and the threading contains many codes, many codes. So what are the codes here? Let's have an example code here. Okay. So you have a bunch of code here. Let's take a look at the producer-consumer implementation. So quite long, a bunch of codes. Okay, implementing the producer-consumer. Okay, I don't ask you to read ahead. Okay, I will ask you to first download it. Okay. Today I will post up the POSIX notes. Okay, you can read ahead by yourself for a while, play around with the code. All code are safe to execute. Okay, there is no hidden fault bomb. Okay, yeah, you should always ask this question. Hey, you release something. Is there any hidden fault bomb? No. Okay, Yeah. If yes, I will tell you. Okay. Like some people always complain about me that in examination I write hidden fault bombs and this is the year I and the year I plus one they get the past paper and try to code those program, then they have big problem. Okay. Yeah. But anyway, you can go ahead and download it. Okay. The notes is already there. I should put it up already. Where is it? It's actually hiding here. Yeah, it's already there. It's hiding here, but I didn't put up the link. Okay, but you can guess. This is part 6. Okay, I remember I also put up chapter 3 already. All right, actually all things are there. Okay, so I just don't put up the links. Okay, you can download it, execute it first, and get a sense what is threading. Then we will talk about threading in the next week. Okay. And last time we talked about the makeup class. The makeup class, we set up our makeup class schedule already here. I already reserved a room. I will also make an announcement about it. Any problem with this date? Okay. Last time some people said that we go through iterations and find this date. Should be okay, huh? Okay. So this is